Yes, so hello everyone once again, and I will be talking, first of all, I would like to thank Emeric and Suhaib and Vladimir before. There was a lot of introduction, which saves me a lot of time. And yes, this work is joint work with many people, and in particular with Victor Dor and Suhaib, who are here at the conference. That's why I highlighted them. All right. So that's again conformal prediction, and as we discussed before, so we want to achieve certain coverage of our prediction sets, and yeah, so the basic approach starts from some conformity scores, and as we just learned, there might be multiple, really very many variants how you define the conformity score. Then you consider the empirical distribution of the scores. And finally, your prediction set is given in a way that you iterate over all possible y's, and you compare the score with the quantile. And I think one of the reasons for extreme popularity of conformal prediction methods is that they have these nice guarantees, right? So we have a coverage greater than 1 minus alpha, and then we have also an upper bound, and this upper bound is very nice. It's like in statistics we are used to the rates of like 1 over square root of n, or even worse in many cases. And here we have 1 over n, so like wow, that seems to be super good. And generally it looks like you may think that's too good to be true, but of course, the quality of your resulting confidence set is directly determined by whether your conformity score is good or not. So if your conformity score is a random number, then the resulting set, well, you will always have this marginal validity, but the resulting set will be just a random set of labels which just ensures the necessary size. The other remark is that I just mentioned that you have this 1 over n plus 1 rate, but that's just due to the fact that you take expectation over all possible calibration sets. So if you consider the conditional distribution, right? So you condition on your calibration data, then as was showed by Vladimir and by some other people quite some time ago, sorry, I don't have a reference here, so the standard result is an expectation over the calibration sets. But if you're conditional on calibration set, then you have the certain distribution, and actually conditionally on the calibration set, you have an error term of 1 over square root of n. So no free lunch here, so it's not something very special happening. And that's important, that in practice you will have a particular calibration set, and you may expect your error to be of this order and not of the order 1 over n. All right. So, and what is really desirable is to go beyond marginal coverage. So, if I have a data like that, my marginal set, well, it still will be valid, but it will be not informative. It will be not adaptive. And ideally, I want something like that for this data, where the width of your confidence interval is adaptive to x and to the distribution of y given x. And as Emeric said before, standard split conformal prediction doesn't achieve that. We have a constant width of the interval. All right, and yeah, so what we really want, we want to be conditional. However, that's not possible without further assumptions. That's quite an intuitive result in this framework. However, in practice, it is sufficient to construct sets with approximate conditional validity, because anyway we have variance due to the calibration, to the choice of calibration set, and so on. And those of you who have attended my talk at the previous workshop, which was online, I was talking to one way how you can approach conditional coverage, and you can assume that you have access to some approximation of your conditional distribution or to the samples from this distribution. So that was the story in the previous talk, and here I will try to attack the same problem from a different direction. And we propose an approach which we call rectified conformal prediction. The starting idea here is as follows. So consider a heteroscedastic regression model, right? And imagine that you somehow know this function sigma of x. Then what you can do, you can transform your scores in the following way. I use here this notation f minus 1 tau of x. Why? Because I want to relate it to my framework, which I will introduce shortly, where I will consider the general family of functions f, and will choose and will like modify my scores. But the running examples which you can have in mind is this one. So you just divide the usual conformity score with a standard deviation, and in this case, what happens? The distribution of the score no longer depends on a point, right? And if it no longer depends on the point, then the marginal validity is the same as the conditional validity. So we get, in this case, assuming that we know everything about our data, conformal prediction gives you not only marginally valid, but also conditionally valid sets. And the idea of normalizing conformal prediction in this way is pretty old. So at least dating to 2008 in a paper of Haris Papadopoulos. And also it has been recently revisited in some papers like by Colombo and Johansson. Okay, so what do we want to tell on top of this? First of all, we don't want to have just, heteroscedastic regression as an example. We want to consider more general transformations over scores. And for this reason, we introduce a family of functions. So we transform score V, and we will have some parameter of this transformation, univariate parameter. So the function family is fixed, but it has this parameter t, which will be defined shortly. And then sometimes for convenience, I will also be using the function f tilde, which is the same as function f, but with the reversed arguments. Okay, I will need some conditions on these functions. Basically, I want this function f tilde. I want to have a point phi, so that function f tilde phi is continuous increasing and surjective. That I would need. And an example is just function f to be multiplication, and the application of this functional will read exactly to this case. Okay. All right. So what I will be actually doing, I will be transforming my scores. And what I want to do, I want to transform my scores. So I assume that I'm given some scores, okay? So you have your favorite scores, you give it to me. I want to make your method better. So what I want to do, I want to transform your scores in such a way, and my transformation will have a parameter which depends on the point. We have a function f with a parameter t, and my t will be given by tau of x. And I want to have a such a transformation tau that's my 1 minus alpha quantile of the transformed score doesn't depend on x. And if it doesn't depend on x, then the conditional coverage and marginal coverage will again coincide for this level alpha. What is important here is that we are not too ambitious here. We don't want distribution to coincide at various points, which might be very, very hard to achieve. We just want quantiles at the particular quantile level to coincide at the different points. Okay, so we want the quantile of some transformed score that does not depend on x. So how we achieve that? We select our target quantile level phi, so it could be 1, it could be whatever, and we consider the transformed scores. So we take our initial scores and transform them with this function f tilde with argument phi. And what is interesting is, I'm not providing a proof, but it's like one line, that in this case, if you set tau to be equal to the quantile of this transform score, then, so it might be a little bit confusing because we have two transformations. We have a preliminary one with function f tilde, which gives me scores v phi. And then I learn the quantile of these preliminary transform scores. Now, what I do with this already given function tau, I transform my initial scores again. And then what happens that their quantile will be equal exactly to phi, which I specified before. So what I achieved via this a little bit involved procedure is that my transform scores have the same quantile at any point x. All right. So that's all good, except that we need to do something with tau. We need to learn it, and how to learn it, we will use quantile regression. So basically, we will consider this scores v phi and learn a quantile regression on this scores for the given level 1 minus alpha. So how to do quantile regression? You can consider a pinball loss, probably with some penalty like here. And to do that, to do estimation, you need some separate set for quantile estimation. So I have a set of some points x prime and y prime, which allows me to learn this quantile function. So what's the difference between this approach and conformalized quantile regression? Conformalized quantile regression is directly learning quantile function on labels y. Here we say, okay, give me any score function, and we'll learn this one-dimensional quantile regression on the scores. And well, you may consider various approaches how to do quantile regression. So basically, which family of estimators to consider. It can be linear functions, it can be non-parametric kernel regression, for example. You can consider deep neural networks, whatever you like and whatever works well in a particular application. And what is nice about the resulting approach? So what is the resulting approach? I have learned my quantile function. Now I transform my scores. And now the transformation varies from point to point. So we have this tau, learned quantile, which guides the transformation. And then I just consider the standard conformal prediction. I assume that I have some set for calibration, separate from the one where I estimated the quantile. And I use just standard split conformal prediction here. Okay. So what we can say about this set? First of all, we can immediately say that there will be marginal validity because all the assumptions of conformal prediction are satisfied, so we immediately get marginal validity. And the question is whether we can say something about conditional validity. And for conditional validity, you can define the following quantity. So this epsilon tau is basically how much you deviate from your target level 1 minus alpha at a given point x. Okay? So that's a natural measure of error in this case. And in our work, we proved the result, particularly in the lower bound, and you can obtain an upper bound in a similar way. So we have 1 minus alpha here plus this term epsilon tau at a test point xn plus 1. And also you have some additional reminder term, which is basically based on the smoothness of a distribution function f. You can make this result statistically you can prove a corollaries of this result for a particular estimation methods. So, for example, if you make a parametric assumption on a quantile, so it can be approximate, it is parametric, then, for example, you can prove that you will have something of the order 1 over square root of n for epsilon, or you can consider non-parametric setup, which will lead to different rates here. Okay, so summary here is that we obtained a method which learns quantile regression on your scores, and then you modify the scores and apply standard conformal prediction over the modified scores. You maintain exact marginal validity, and you can conditional validity, which is kind of explicitly controlled. Finally, experiments, and probably for the sake of time, I will just show this picture. So, well, this picture shows the following. We take some base conformity scores, like in PCP, DCP, or SCP papers, and we modify them with the help of our rectification procedure, and we look on certain like surrogate of conditional coverage, which is called word slab coverage, and we see that while we do not achieve the perfect coverage, like our target level was 0.9, but all the modified methods they improve over the baselines in our experiments. All right, so that's the end of the story here, and we have a little bit of time for questions if you have any.
Thank you very much. Are there questions from the audience? Maybe I have one question. Could you say a few words about this word slab coverage? What is this as a quality measure?
Yeah, so basically it's very hard to evaluate exactly conditional coverage because we don't have access to samples. And what you look on a certain projections of your data, essentially. So you look on some projections of the data, and you look on many random ones, and you look on the coverage, on the worst coverage over these projections, more or less like that. You look like on a strips of your space.
Other questions? Good. Then let's thank the speaker again at the next speaker.